Well, hello there. This is our video on 100N filtered water system. This continues from the circulating raw water system. It's just kind of a quick overview of it. We have some drawings that show this stuff a whole lot better. But basically, you have your circulating raw water comes into the coag pumps. This is on the raw water video. From there, it goes up to a mixed tank. Alum is added, aluminum sulfate. It ran somewhere between 12 to 20 milligrams a liter parts per million. 118 milligrams a liter was what we usually ran at. Chlorine was injected. This plant used chlorine gas, which is no longer used. They went to the hypochlorite solutions, which are a lot safer. They didn't want to add too much chlorine because this water ended up in the demin plant. We had to have enough to kill the biological growth in the system. So the alum and chlorine were added in the mixed tank. The purpose of this was to mix the alum very well with the water. Once the alum mixes, you start with the alum, which is aluminum sulfate, and it has water in it. The aluminum sulfate in the water combines with calcium bicarbonate, and this made basically aluminum hydroxide, which did not stay in the water and had a plus charge. It attracts all the dirt. The dirt has a negative charge usually. So the alum tried to drop out of the water and form what we call flock. It also grabbed all the dirt, so it made a fairly large particle, kind of like snowflakes. So you had to mix it well, and this started the flock formation. Then it went to the coag basin. These are fairly large. I originally had paddles in here. The water would come down the bottom, back up. The purpose of this was try and get most of the flock and dirt, sand to drop out, reduce the load on the filters. This was modified in later years as the flock formation worked fairly well, and it's just easier to take the dirt out the filters instead of have a lot of mud pile up in here. You had to wash these out every year. And there were sand drains and mud drains you'd open up every shift, try and get out all the accumulated debris you could. Downstream of the coag basins, Sepran was added. There's a polyacrylamide. The purpose of Sepran was to improve the filter efficiency. You'd add enough Sepran so that your head loss would get high at the same time as you started getting breakthrough or particulate started showing through the filters. It's kind of a filter aid. So if you had too much Sepran, you'd seal your filters off. Couldn't get water through it. Not enough, you'd get breakthrough. Turbidity would break through eventually. The way the filters worked, they were 13 feet wide by 28 feet long. They were a Wheeler false bottom type filter. You had a concrete floor with little pyramid-shaped depressions full of ceramic balls. Then there was different layers of gravel across this, and 24 inches of anthracite hard coal. Top of that, you had your surface sweeps. These would run, they had nozzles, and the purpose was to break up the surface layer so you didn't have mud balls. They would run for your backwash. You wouldn't want to run these while you're backwashing hard because you'd blow the anthracite out. Wash water troughs, they sat about 2 feet above the bed. This was the lowest the level ever got. That way when you backwash, there's a little bit of water in here to keep from blowing your anthracite. So the water would come up out your wash water troughs and out the waste. This is the top view of the filter. This would be the side view. Your wash water troughs come across. This here was an open channel. Inflow would drop in here. Water would go here and run out the wash water troughs so you didn't disturb the bed. Backwash drain was on the other side of this. So this was the lowest level the filter came while you're backwashing. From here, your waste water went to the backwash sump. Had two pumps, pump it out to a holding pond out back. Water from here went to the clear well. There's a flow control valve. These were rapid sand filters. So they could take up to 10 gallons a minute a square foot, but that was absolute max. Usually ran a whole lot less. The slow sand filters could usually run only a fraction of a GPM a square foot, but adding the alum and getting the flock coagulation going, it greatly improved the efficiency of the filters. I believe when the head loss hit 8 feet, we'd backwash these, or if you had turbidity breakthrough, and also went on hours too. I think 48 hours was about it. From here, I went through, like I said, a flow control valve to minimize the flow across the filter. I dumped into the clear well. Your clear well pumps pump to the filtered water tank, held 850,000 gallons. This was the secondary supply for the ECS. It fed the high lift diesel pumps. There was a valve, 817, had to be opened. Once the demin tank got down to minimum level, this could also feed the fog spray pumps if need be. From the tank suction, this ended up in the 182 high lift pump house building. You had your potable water pumps and chlorine was added. That was a hypochlorite system. You had your low pressure filtered water pumps. These are really the main filtered water pumps in the plant. Low pressure filtered water, it fed the high pressure filtered water pumps. The filtered water plant used high pressure water to control the valves. They're brass cylinders, so most of these, the backwash valves, drain valves, effluent valves, they were all water operated. Used water pressure to run them instead of air. So this plant didn't take much air. The influent valves, they were air operated, but everything else was pretty much ran by water. It ran the demin plant feed. From here, the water would go to the demineralizer plant. Fed all the ventilation systems for basically cooling through pads pulling the air through. Diesel jacket water, the bottom insulation cooling in the reactor. Your main gas condensers, this was for the reactor gas. The helium went through compressors to remove any moisture out of it and to cool it. Had the 184N miscellaneous cooling uses, 181, 109, 105 miscellaneous uses. Fed a lot of hose water bibs. There were 4 of the low pressure filtered water pumps, 3,700 gallons a minute, about 260 foot head. It's about a little over 100 PSI. From here, it went to the high pressure filtered water. These just ran 1,200 gallons a minute, about 300 PSIG. The main purpose of these was the control rod heat exchanger cooling and backup rod cooling if you lost the normal problems with the control rod cooling system. Other than that, this is kind of a quick overview of the filtered water system. We have a lot of drawings of these which show this a whole lot better than this whiteboard. This is kind of a quick overview of the system. It's one of the more simple systems. The filters, they could put out 15,000 gallons a minute if they had to. Normally just maintain tank level. So when you backwashed, you'd pump out of the clear well. It'd flow back in here and up through the bed. The process for backwashing the filters, first you'd close the influent valve. It fed in here. Let this drain down normally. Then you got down lower, you'd close the effluent valve, open the waste valve, level drain down to the top of these. Then you would start the surface sweeps. I'd go through and mix up the top part of the bed. Then you open the backwash valve. I'd come off the clear water pumps, and it was also flow controlled so you didn't blow the bed apart. One problem with these filters, if you ever had air in here and you open the backwash up real quick, you could blow this bed apart, mix up the different layers, then you have to go back in and take it all out and rebed it. Too much backwash flow, anther felt would get washed out. Run the surface sweeps. Too much where you're backwashing could take some of the anther felt out. Usually it was high enough water pressure held the beds pretty good. So you had to control the effluent, how much water went through these beds, and the backwash, how much water come up through here. You need enough water to expand the bed and wash out all the flock and dirt. The Sepran did a pretty good job of holding it in the bed. Without Sepran, you'd have a lot more breakthrough on these, but it did work well, as long as you didn't feed too much and seal the bed off. Other than that, these little plants really work fairly well, as long as you had the chemicals set right. If you added too much alum, you just waste alum, you get real heavy, big flock particles. It dropped out pretty fast. I mean, it just wasted alum. If you didn't have enough, you'd have really small flock. Some of it would be almost too small, not make it through the filters. So the big thing on filters, you're watching the head loss and breakthrough. If any dirt starts getting through here, you check the turbidity. If your turbidity started climbing, then you'd have to backwash. Other than that, we'll go to the drawings that make a lot more sense of this. Okay, these are the drawings of the filtered water plant. These were a lot better than anything we could do on the board. The board was just a one-line diagram of this. We have the chemical mix tank. Raw water come from the coag pumps. Alum and chlorine were added. This is like a 30,000 gallon tank, and it mixed up the alum, chlorine, and raw water. From here, it went to two different coagulator basins. Originally, the water would come in down the influent channel, and these were holes in the bottom, pipes that went down to the bottom. These are the paddles. These are designed to go real slow and produce a really good flock, trying to get the water to slowly mix. I didn't want to mix too fast or you'd shear the flock. So the object was to make large flock particles that would drop out of the water. So a lot of the filtration was supposed to take place in the coagulator basins. They're like desludging headers and different things that you'd open up every shift, try and get out some of the flock buildup, and also the sand would drop out back in here. Towards the end, there are holes cut in these, and the water pretty much just went straight across. The collector flumes had little holes in this, so it took an even flow across the whole basin. If you just had it overflow, most of it would come off of here, so I think they're like inch diameter holes. So the purpose was just to get an even flow of water across the basin down the collector flume, and from here it would go to the filters after this. It was designed so you could isolate one basin or the other for cleaning, maintenance. But this was really a great system, but it was just a little bit overkill for the Columbia River water. It was pretty clean and didn't need a lot of removal of particulate. This would be good in really dirty water. You had your sand removal header here, they're shown, and this is kind of a sludge removal. This one is kind of the end view. This is where the water would enter. It'd go down the pipes to the paddle wheels. And from here, it'd come back up in the basin, then it would overflow. They're showing like 2 1/8 inch diameter orifices to collect the water with. So it's kind of a complex item, but it would produce really good flock. Like I say, we found that we just cut holes in this and timed the water come across here slowly. You'd produce really good flock development, and it was easier just to backwash the filters and get rid of it. Just kind of a quick drawing of the pre-treatment filtration system, coagulator pumps, basically flow control valve, level control valve, feed the chemical mix tank. feed the 2 coagulator basins. The effluent from this was the influent for your filters. 6 filters sat here. You had your filtered water flow control valves. That way you wouldn't pull too much water through a filter. It had to be controlled, or you could overload the filters. If the flow is too high, you'd have breakthrough. The turbidity would go through the filters. Drop down a flume, went out to the clear well, a 200,000 gallon clear well. From here is pumped to the filtered water storage tank. Like I said, this is from the 182 building, low pressure raw water pump. This ran all the hydraulic control valves, Palmer sweeps, we call them surface sweeps. Also, water went to the chlorinator, and they used 1-ton cylinders of the chlorine gas and went through a chlorine injection system. After working with ammonia, you weren't too worried about ammonia. You could smell it, not a big deal. Chlorine would just plain kill you, so it was a pretty dangerous system. Everybody now has gone to the hypochlorite systems. This is the filter. They were Wheeler false bottom filters. You had a concrete slab, and there's a ceramic thimble cast in the bottom. Then in here these balls sat. I think this here shows 5 large balls, and then there's the little balls set in around the top here. And on top of this you had different layers of gravel. Each layer of gravel is about 3 inches. I had 6 inches of sand. Then you had your anthrafilt, or basically anthracite hard coal. There's like a 1/4 inch size aggregate of the anthrafilt. It was lightweight. The theory was when you backwash, this bed expands and all the particulate is removed. This is where you get in trouble if you have air in here or too high of a backwash rate. You could launch these balls up into the beds, mix the beds up. At that point, you got to tear the whole thing apart and rebed it. This shows the Wheeler false bottom, the depressions in the concrete. Underneath this was empty. This is where the effluent water, or the filtered water, would collect, and it'll go through the control valve to the flume and then out to the clear well. This shows the inlet and waste flume. Here's your influent valve. It was like a plug valve that would open. Water would come down here. You had your troughs where it evenly distributed across. Your waste valve sat on the other end. Effluent wash was here. Normally the water would come out of the filter here, but for backwashing it'd come in through the same line. You needed adequate water flow to expand the bed and remove the drip. You didn't want enough to blow the anthrafilt out of the filter down the wash troughs. This is just a cross section of the filter. You had your Palmer surface sweep set right on top of the bed. They weren't very far above the bed, maybe 6 inches. You had to go down there and clean nozzles. Occasionally anthrafilt would get in them. They covered a 12-foot diameter each one. Here's your wash water troughs. They sat right above that. I think it was like 2 feet off. So when you backwash the bed, you didn't want the anthrafilt to get up to here. You didn't want to expand quite a lot and clean it. This is a better picture of the side view. You have your influent valve. Now I dumped down the gullet. It ran right across this part of it. These are the wash water troughs, surface sweep, effluent valves. You can see these were little different cylinders. These use water pressure to run. Like I said, a lot of this plant ran off of water pressure. The rest of the controls was Bailey, 3 to 27 psi for the control valves. Recorders usually ran 3 to 15 psi. This is before the days of the PLCs and way before the Allen Bradley logic controllers when this was built. So everything was Bailey, and all the instrumentation ran off of air pressure. The controls were pretty intricate using the air pressure. They had cams that you could cut to change your integrals, and it was all mechanical, but it worked reasonably well. So you have your wash main. You had to control the flow going in through the bottom of the bed so you didn't blow the bed up, and also control the effluent coming out. This is a picture of the control panel. Here are your 6 filters. These were the control valves, controls to run the valves manually. This chart recorder showed the DP and also turbidity. Each filter had a turbidity meter so you could watch the effluent turbidity. You have your clear well depth indicator. This is basically had your different recorders for storage tank, wash water flow, mixed inlet flow. This is the water coming into the mixed tank or the plant. And bypass we never use because everything's being filtered. Pump start switches, more pump switches. This here was for the auto start of the filter. Your DP, I believe, got to 8 feet, head loss across the filter. Pushing these buttons and it ran automatically. But like I was saying, this is before PLCs. They used rotary switches or a carousel type switch that would time and then move to the next one. You had your timers for surface sweep and backwash, and you could also set the backwash rate. In the wintertime the water was more dense because it was colder, so you didn't need quite as much backwash flow, whereas the summer you had warmer water. You'd run a little bit higher backwash flow rates. And if your head loss climbed up too fast and you didn't have any turbidity coming through, that'd be a sign you had to back off the separator in your filter aid. Or if you started having turbidity show up in the effluent before your head loss chart grew very much, you'd have to add more separator. So if you're having to backwash at about a 3-foot head loss because of the breakthrough of the turbidity, you needed more filter aid. So that's pretty much the panel layout in the filtered water plant. Other than that, it was kind of a simple, fun little plant to run. It produced pretty good water, and you could produce up to 15,000 gallons a minute if it really had to. It seems like it normally ran about 2,000-3,000, something like that, because you're also feeding the demin plant and a bunch of little different type of cooling equipment around the plant. Anyhow, that concludes this. Hope you liked it. This is more of a historical overview of the plant, because in the near future all this stuff will be gone. Nobody will know anything about it. Well, take care.